The next thing I'd like to talk about is a very interesting characteristic that has to deal with the reflected ray. Remember, for an incoming ray, in general, we'll have a reflected ray and a transmitted ray. And the characteristic has to do with the polarization of the reflected ray. We talked about polarization back in the first lecture of this unit, and remember the polarization deals with the direction of oscillation of the electric and the magnetic fields for an electromagnetic wave. Let's just remember what we said. Let's imagine we have a wave traveling in this direction, and we can think about that as our ray, and that's our velocity direction. The electric field and the magnetic field, but let's just focus on one of them. We'll talk about the electric field. The direction of the oscillation of the electric field has to be perpendicular to the velocity direction, which means the electric field must oscillate in this direction or this direction or this direction or into the board this way. So basically the electric field can only oscillate in an up and down direction, an in and out direction, say in and out, a circle with an X or a circle with a dot, or some combination of those. So anything in this direction, but it cannot have any component in the direction of the velocity. So along the ray, there cannot be any component of the oscillation of the electric field along the direction of the ray, or opposite the direction too. Let's imagine that we have a particular orientation for our incoming ray so that the reflected ray and the refracted ray are perpendicular to each other. So I want to imagine that this is a 90-degree angle. Now, the oscillation in the electric field for the incoming ray, whatever direction that is, and I'll just draw it like this, but remember it can also be going in and out of the board. That electric field comes down and then breaks apart into two different parts of the electric field, one that goes along the reflected ray, one that goes along the refracted ray. So this ray will have some oscillation, let's say in that direction and in and out of the board. This ray will have some direction for the electric field, say that way or in and out of the board. And this electric field must equal this electric field plus this electric field. So when it splits apart, the electric field splits apart, so that this E plus this E must equal that E. Okay, let's think about what is a possible direction for these electric fields. We have made the assumption that the reflected ray is perpendicular to the refracted ray. So this part of the electric field that is not the part going in and out of the board, but perpendicular to that, would be in the same direction as the direction of the refracted ray. Well, this direction, although not in the same direction as the incident ray, at least is partially in the direction of the incident ray. Well, how would it be possible for this electric field to equal this electric field plus this electric field? If this electric field could have a component that canceled out the part that's in the direction of the incident ray, then that would be okay. But we know that this electric field must be perpendicular to this direction. That means this electric field can have no component in this direction to cancel it out for this ray. The bottom line is that this ray cannot have any electric field in that direction that corresponds to the direction of the refracted ray. It can only have an electric field that oscillates in or out of the board. That's the only possible direction of oscillation for the electric field, because there's no other way that this electric field plus this electric field could equal this electric field with that orientation. Well, what does that mean? If this electric field can only oscillate in and out and not this way, that must mean that this ray is polarized. It has a polarized electric and magnetic field. Well, that's very, very interesting and very surprising. But as a matter of fact, we can demonstrate that. Let's take a look. Here I have a flashlight and a polarizer. And the first thing I want us to notice is that when I send the flashlight light through the polarizer cuts down on the amount of light. However, when I rotate the polarizer, notice nothing happens. The amount of light is still the same regardless of the orientation of the polarizer. What is that telling us? That's telling us that the light initially coming from the flashlight is unpolarized. When it goes through the polarizer cuts down some of that light, but it is independent, the amount of light going through is independent of the angle of the polarizer. You should be able to say how much light actually makes it through the polarizer, what's the intensity compared to the original intensity. Remember, when unpolarized light goes through a polarizer, we get half of the original intensity. Now I'm going to take this light and I'm going to reflect it off of this block of plastic. I'm going to reflect it off of the plastic onto the whiteboard. And we're going to look at the reflected light and see if that is polarized. So here we go. I'm going to reflect it off of the plastic and onto the whiteboard. There we go. Now I'll take the polarizer and notice that again it cuts down some of the light. However, if I rotate the polarizer, now I can completely cut out all of that light passing through the polarizer. So now what does that tell us? That tells us that the light that is reflecting off of the surface must be polarized. The fact that we have this reflection taking place is polarizing the light. Let's see if we can figure out at just what angle would we have to have our incident ray in order for our reflected and refracted ray to be perpendicular to each other and give rise to completely polarized reflected light. The incident angle that gives rise to this condition, such that the reflected ray and the refracted ray are perpendicular to each other, is called the Brewster angle. Let's see if we can figure out what that value is. We know the reflected ray is going to reflect at an angle that's equal to the incident angle, so we know that this angle must also be the same angle, the Brewster angle. We know that these two rays are perpendicular. Let's see if we can figure out what the refracted angle must be. We'll call that theta sub 2. We know from this condition right here, this straight line along the normal, we know that theta b plus 90 degrees plus theta 2 must equal 180 degrees. Subtracting the 90 and subtracting theta b, we have that theta 2 must equal 90 degrees minus theta b. Now let's stick these angles into the law of refraction and see if we can figure out a relationship. We know that n1 sine theta 1 must equal n2 sine theta 2. n1, the index of the first medium, times sine. Now theta 1 we want to be the Brewster angle, theta b, equals n2 sine theta 2, and theta 2 we know is 90 minus theta b. But what is the sine of 90 minus an angle? Well, it's cosine of that angle. So we can write this as cosine theta b. Let's divide both sides by cos theta b, divide by n1, and we have that sine theta b over cos theta b equals n2 over n1. Now what is sine over cos? That's tan. And there we go. We have a very simple relationship that relates the Brewster angle, theta b, to the two indices of refraction, n2 over n1. Let's stick some numbers in here. Let's imagine that we have an air-water interface. So n1 is for air, n2 is for water. What do we get? Well, we get tan theta b is n2 over n1, 1.33 over 1, which is 1.33. Theta b will then be the inverse tan of 1.33, or theta b is 53.1 degrees. What does that mean? That means if we have a ray coming in at 53.1 degrees, it will reflect and refract, but the reflected ray will be polarized. And it was that polarized light that we just saw in the demonstration. Very good. Now, one thing to keep in mind, how do we remember which one is N1, which one is N2, which goes on the top, which goes on the bottom? Well, if you can remember the rule that we used for total internal reflection for the critical angle, it's the same rule that we can use for this one. Remember, what I said for the critical angle for total internal reflection was that the ray starts out in the denominator. In other words, the index that goes in the denominator, that's where the ray starts out. Well, in this case, the ray starts out in N1, and N1 is in the denominator. So if you just remember, either for total internal reflection for the critical angle or for the Brewster angle, the ray starts out in the material that's in the index in the denominator. I just think of it as the ray starts out in the denominator. If you can remember that, you will make sure to get the right order of indices. Now, there's one thing that's a little bit different with the Brewster angle than for the critical angle. Remember, for the critical angle, you could only have total internal reflection in the material with the larger index. So there's only one critical angle for a particular interface. In other words, you could have a critical angle for a ray in water bouncing off air, but there was not a critical angle for a ray in air bouncing off water. That is not true with the Brewster angle. You can have a Brewster angle for a ray in air bouncing off water, but you can also have a Brewster angle for a ray in water bouncing off air. So you do have to be careful. It's not always going to be the larger on top or the smaller on top or something like that. With the Brewster angle, you can have either one. Great. One more thing I'd like to take a look at before we finish up. So far, we've been talking about refraction at flat surfaces. Next time, we'll talk a lot more about what happens when we have a curved surface, but I'd like to talk about just one simple curved surface just for a second, and that is, what about a sphere? Imagine we have a round material, and we've got light reflecting and refracting off of it. What happens? Well, what will happen is an incoming ray will refract at the front surface, go into the sphere, reflect off the back surface, refract off the surface again, and come back out. This is one possibility for the light to refract and reflect. Now, one thing I told you at the beginning of class is not exactly correct, and I need to clarify that. I said that the index of refraction for a material tells us the ratio of c over the velocity of light in that material. But the fact is that different wavelengths of light actually can travel at slightly different speeds in the same material. What that means is that different colors of light could have different values for their index, different indices. What does that mean? That means when light enters a material, the different colors will refract differently. White light is actually a combination of all of the colors of the rainbow, red, orange, yellow, green, blue, indigo, violet. So when white light enters a material, it sometimes separates those colors because of the different amount of refraction. For example, the path I've drawn here might be the path that, say, blue light takes. But if this were actually white light, a combination of all of those colors, what would happen to red light that's along with, or part of that white light? When it comes in, it doesn't refract quite as much. And it ends up striking the sphere at a different point. It then reflects off differently and then comes back out in a different direction. So the sphere will actually separate out the colors. Well, have you ever seen something like that? Well, that's how a rainbow is formed. When it rains, there are spherical droplets of water left in the air. And if the sunlight, if here's the sun, strikes those droplets, and you are standing in just the right place with the sunlight striking the droplets and bouncing back into your eyes, you will look in different directions you'll look in different angles and see the different colors. So the rainbow seems to be separated out in different colors. Very, very interesting. Now, there's something I want you to look for the next time you see a rainbow. It turns out that, for example, if you look, say, at this angle, at any angle, you will see the blue light. And at any angle for this one, you'll see the red light. So that a rainbow, the shape of a rainbow, is actually a perfect circle. My question is, what is at the center of that circle? The answer is not a pot of gold, but it turns out because the sunlight has to be shining from behind you to make the rainbow, the direction towards the center of the rainbow is the direction, if you connected the center of the rainbow through your head, that is exactly where the source of light would have to be. That's where the sun is. So if you look at the center of the rainbow, what you will see is the shadow of your head. So the next time you see a rainbow, see if you can see it, figure out if that's a circle, where's the center of that circle? At the center of that circle, that's where the shadow of your head will be. Very good. Well, I hope this was interesting. Next time, as I said, we'll talk about what happens when light refracts off curved surfaces. We'll look at it in a little more detail than this. I'll see you next time.